Welcome to topic 8 of CP1. In this topic, we are going to cover DFS, depth first search, and flat fill using DFS. So let's start with the example problem. This is a LeetCode problem called max area of island. So we are given a 2D array grid of zeros and ones, and the island is defined as a group of ones that are connected. So these ones represent the land, and here by connection we mean the four-way connection, so horizontal or vertical. And you may assume that all the four outside edges are surrounded by water. And the goal is to find the maximum area of an island in this given array. So the parameter in this problem is the grid length and width do not, height and width do not exceed 50. So let's look at the example. So this is if this is the input, I use the blue background to mark the ones. So think about this example, what will be the answer? So the answer, I believe, should be 6. So in this picture, we have 1, 2, 3, 4, 5, 6 separate islands. And the biggest island is this one, which area of 6. So note that this one and this one are not considered to be connected because we only consider four-way connection. So up, down, left, right. We don't consider diagonal. So some problem will consider 8-way connectability. So then in that case, if we define as 8-way connectability, this will make a bigger island. So how do we compute the answer? If we look through the array one by one, the array cell one by one, when we see a 1, we want to find out the size of that that island. So we do that by doing a search to find out all the things that are connected to it. And this search can be done using a depth first search, DFS, or it can also be done using BFS, which we'll cover in the next topic. So one way to do DFS is to use recursion. Let's look at the code. So this is, I think this is a driver code. This one does not do the DFS call. So this will make a call to the DFS. But let's look at the driver code first. So we get the size of the grid and the initialize answer to 0. We loop through all possible cells. If its value is 1, then we're going to call DFS using this grid. And this DFS will return the area of the island. So depending on the problem, a DFS call may be returning something, or maybe it doesn't directly return something. Instead, we just modify the grid or change some other state. But here, we can make it just return the area. And then this will return the area of the island, and then we just use this to keep track of the maximum ones. So yeah, I guess in this case, the DFS should both change the grid and return the value, because once we visited the island once, when we see another piece of the island, we don't want to visit it again because we already know its size. So this is a DFS code. So here we have input ij here. So this is the very common pattern is you do check at the beginning. So we check first I and j are within the boundary, and if it's within the boundary and it's not 1, then we don't. If it's so, we want to do things only when it's in the boundary and it is 1. So because we don't want to do anything that's 0, and also yeah, so we want to only visit these cells that have value 1. So these checks, if it's outside the boundary or the value is not 1, will simply return. So if it is 1, we want to essentially do this, we want to visit all the neighboring cells. So I minus 1j, I plus 1j, ij minus 1, and ij plus 1. And we calculate all the area that we can reach from this neighboring cell, and then we add 1. However, we need to make sure that when we go to our neighbor will also execute this code. We don't go back to visit this node again. So each time when we visit the cell, we have to change the state somewhere so that we will not recursive call on this neighbor cell on this cell again. So here I change the value to 2, and then because of this check, when I visit this again, it will simply return. I will not do this body again. So initially the each cell will be either 0 or 1. After DFS calls, all the ones the ones that are rich should become 2, and this returning number will count how many number of ones we have encountered. Yeah, and DFS returns 0 when the index is out of the boundary. I guess this actually is a typo. This should be contains 0, or has been already visited. Has already been visited will have value 1. Okay, so yeah, so this is DFS. So let's look at the code and see why does this code terminate. And also get the complexity. What's the complexity of this code? So the reason you terminate, it's this line, basically these 2 lines. So anytime we enter a cell, the value will be changed to 2. And next time if we visit this cell again, we will directly return. So therefore, we cannot keep visiting a cell again and again. So another question is, at most how many times would DFS ij be called for a particular value of ij? So let's say how many times could DFS 2, 3 be called? So I equals 2, j equals 3. It's more than once, because of this. But it's just that the first time it's called, we may go down here if the value is 1. But after the first time, we will always return at line 4. So we will not try to process the node again. So encourage you to find out the answer. How many times this is called? So the answer is at most 5 times, and at most once from the main function, the max area of island. Because when you see this 1, it will call this, and from this code here, each cell can only be called once. So that's for sure, because we're just going through each one. But it can also be called from DFS, but it can be called at most 4 times, basically by its 4 neighbors. So while we are visiting its 4 neighbors, we may call this DFS with this ij. So it will be called at most 5 times. So then therefore the complexity will be of DFS will be linear in the size of the grid. So this is a skeleton pseudocode for DFS in general. So inside DFS call, generally the first thing is we check whether it's out of bound, whether the cell is wrong or whether it's already visited. And then we should update the information to indicate that this cell has been visited. So the next time the check here will find that out and return. And then we recursively call DFS on all the neighbors. And then in the end, we will do whatever needs to be done. So in this particular problem, we actually add up all the return value from DFS neighbors and add 1 to it and then return. So in general, DFS is a powerful algorithmic technique. It can be applied in other kind of a graph, and can also be applied in searching, generally searching for a solution. But in this topic, we're limiting ourselves to grid with cells, because I think once we understand how to do DFS with this, then the other understanding this how to do DFL is important. So let's just understand how to do this in this context. In the last topic, we will be using actual graphs rather than this implicit graph defined by grid cells. And so you'll be practice using DFS on graph there. And another thing is the DFS is use recursion. So the recursive function call will use stacks. So each time you call the function, you will allocate some stack space to store the local variable and the arguments and so on. If the connected component is too large and the recursion goes too deep, there's a possibility that we'll run out of stack. So depending on how the environment is set up, the depth that's sufficient to reach to generate out of stack error is different. So I think this 7000 is my experience running Java some version on local machine. So it will depend on the runtime environment. So if that is the issue, if this stack space is the issue, then we can implement DFS using an explicit stack, which we will do in one of the later problems. Or we can also, instead of using DFS, we can use the BFS, which will be covered in the next topic.